This is Mr. Martin. These are video notes for Precalculus Honors. We're continuing with section 3.2, talking about logarithmic functions and their graphs. And in this video, we're going to specifically talk about the natural log. So keep in mind that all the properties that we talked about for common logs in the last video are also going to apply for natural logs. So for a natural logarithm, for x greater than 0, we're going to have y is equal to natural log of x if and only if e to the y is equal to x. So keep in mind, this is just like our property that we did with common logs, where we had y is equal to the log base a of x, and then if I wanted to rewrite that in exponent form, I would have a raised to the y is equal to x. Okay, we're just doing the same thing. Again, this is a log base e of x. We just write it ln for natural log. That's our abbreviation for it. So let's go ahead and use our properties of natural logarithms to rewrite each expression. So remember, the natural log and e, those are inverses of each other, just like log base 10 and 10 to raised to some number are inverses of each other. So for this first one, the natural log of e to the 1/2 is simply going to be 1/2. So if we rewrite this as log base e of e to the 1/2, and then we let that equal y, if we rewrote it, we would have e to the y is equal to e to the 1/2, and using our 1-to-1 property, y would have to be equal to 1/2. So either way you want to think about it is fine. Again, the natural log and the e basically cancel each other out. Then for part B, we have e to the natural log of 7. Again, the e and the natural log cancel each other out, so that's just going to be 7. And this one is a little bit different, so we're going to use one of our other properties of logs where you can take this coefficient and we can move it up to an exponent. So I'm going to rewrite this as the natural log of 8 cubed, and then I'm going to rewrite 8 as 2 cubed. So the 8 becomes 2 cubed, and then that's cubed again. And then if I simplify that, we end up with the natural log of 2 to the 9th. So again, remember that property that we can take that coefficient and make it an exponent. We can also take the exponent and move it to a coefficient. And we'll look at stuff like that soon. Alright, moving on. We want to find the domain of each. So the natural log curve has a general shape that goes like this. This is going to be 1, 0. So we see that our domain values, there's no x values that are going to be less than 0. So what that means is for part A, that means that x minus 4 has to always be greater than 0. It's never going to cross that line here. So that means that x has to be greater than 4, which means our domain would be from 4 to infinity. Okay, we need to find out what values will make this positive. Alright, and then for part B, we know that 5 minus 2x has to be greater than 0. So negative 2x is greater than negative 5. And x has to be less than 5/2. So if we took a look at the graph of this, it's actually going to be flipped over the y-axis. It's going to open up this way, which is why our x values are going to be less than 5/2. Alright, for part C, x cubed has to be greater than 0, which means that x is going to be greater than 0, let's write our domain over here. So our domain is going to be from negative infinity to 5/2. And then for part C, our domain is going to be 0 to infinity. Now for part D, there's a couple things we have to consider. We need to make sure that x plus 2 is greater than 0, which means that x is greater than negative 2, but our denominator cannot equal 0. So x cannot equal 2. So for our domain, we're going to have negative 2 to infinity, where x to 2. Alright, moving on to example 3, let's look at a few graphs. So these two graphs are inverses of each other. So once we graph e to the x, we're just going to switch the x and y coordinates to get the natural log of x. So let's make a small table for e to the x. Let's just look at 3 different values, x and y. So let's look at 0, 1, and 2. And let's come over to our calculator here and figure out what these are. So you see I have e to the x over here, so I hit second already. And then e to the 0. Well, e to the 0 is just going to be 1. And then e to the first, we know that value. That's going to be about 2.7. And then e to the second, it's going to be double that, but we could plug it in anyway. E to the second, that's going to be about 7.4. So we know the general shape of an exponential is always going to look like this. So let's graph these. We have 0, 1, and we have 1, 2.7, and 2, 7.4. So somewhere about there. And we'll sketch in our curve. And then we're going to reflect this over the line y equals x. So we're going to find our new x and y values. So now our x values are what our y values were for y equals e to the x. So we have 1, 2.7, 7.4, and then 0, 1, and 2. So I have 1, 0, 2.7, 1, and 7.42, 7.42, somewhere about there. And again, we'll sketch in our curve. And we can see that these are reflections. And there are our 2 graphs. Alright, so I'm going to end the video here. If you have any questions, make sure you ask. Go ahead and give the checkup a try. And we'll see you in the next video.